hypothesis tests about the difference between two population means, or more commonly known as a z-test or t-test for two population means. Two sample tests come in several varieties, and we will cover all of them in this playlist. In our last set of videos, we learned how to form confidence intervals and conduct hypothesis tests for single population data. For example, let's say a manufacturer claims that a container contains 64 ounces of orange juice. We could take a single sample of bottles and then construct a confidence interval for the mean number of ounces and conduct a hypothesis test where the null hypothesis states the mean equals 64 ounces. We don't expect the mean to be exactly 64 ounces, but very, very close. In a two population scenario, we compare not one, but two population means against each other. So in our orange juice example, we could test the bottles in two different factories to see if the mean number of ounces in each bottle is the same or different across the two factories. Note, we're not trying to compare the means against an assumed value, we are comparing them against each other. So the means could be equal to each other at 60 ounces, but that would be very, very bad given that the label claims 64 ounces. Many students I've worked with learn two sample tests in class without actually knowing what they are or why they even exist. So this video offers a solid conceptual foundation about two sample tests comparing means using illustrations and graphics. So if you're new to these techniques or are still trying to figure out exactly what they even are, this video is for you. So sit back, relax, and let's go ahead and get to work. To fully understand the topic of this video, you will need to have had experience with and/or knowledge of the following concepts. What the critical z-values are for a given alpha level, both in the two-tailed and the one-tailed scenarios. So basically, you need to know how to read a z-table. How to calculate test statistics. What the rejection and non-rejection regions are in distributions. What the null hypothesis and the alternative hypothesis are. And once you conduct your test, how to interpret those conclusions. So this video is an extension of these topics in the context of analyzing the difference between two population means. Now much of this was discussed in the one sample case, so we're just carrying that over into the two sample case. Now when we are looking to differentiate or compare two distributions, there are two primary characteristics we can analyze. We can look at the location of their means. So where is one population's mean relative to the other? Are they far apart or are they close together? Do they line up? The other thing we can look at are their variances or their spread. So does one of the populations have a higher variance or higher standard deviation than the other? Is it wider in its distribution or is it narrower? So let's take these concepts and actually look at it in the context of a problem. So let's say you're the manager of two call centers near Bangalore, India. These centers focus on in-depth problem solving for clients. Therefore, the calls last approximately 12 minutes. Each location has its own employees, its own management, and its own work culture. They are independent of each other. As part of your performance analysis, you wish to see if there is a difference in the average call length between both locations. Difference length between the two call centers. So we have call center 1 over here on the left and call center 2 over here on the right. Now each one has its own population mean, so mu sub 1 and mu sub 2. Now we are given, or from previous data in the past, we know the population standard deviations, or the sigmas. Now in other types of problems, and actually in the problems that are most prevalent, we do not have these sigmas, and therefore we have to estimate them using sample data. But for this type of problem, we are going to assume that we have the two sigmas. So for call center 1, the population standard deviation is 1.2 minutes, and for call center 2, the population standard deviation is 1.5 minutes. So what is our assumption here? Remember in the previous slide, we were assuming the difference between these two cost centers, these two means, is 0. So mu sub 1 minus mu sub 2 equals 0. Now what about independence? Now these two centers are independent of each other. Now that's important when we're doing an independent samples z-test or a t-test. We are assuming that these populations are independent of each other. So as we established in the previous slide, we're going to assume that they are. So what about the hypothesis formats and the regions? And this goes into actually writing the hypothesis and understanding what it means. So in our first case, our null hypothesis is that the difference between the two means equals our hypothesized difference, that is d sub 0. Now most of the time, d sub 0 will actually be 0, but it doesn't have to be the case. The hypothesized difference between the two means could be really anything. Now the alternative in this case is that the difference is not equal to d sub 0. So it's just the opposite of what our null hypothesis is. Now as far as the distribution goes, it's going to be a two-tailed test, because when we say that it's equal or not equal, that could mean that it's below or above. It could be positive difference or a negative difference. Therefore, we use the two-sampled case. Now we also have the situation where the difference between the two means is less than or equal to our hypothesized difference. So mu sub 1 minus mu sub 2 is less than or equal to d sub 0. Therefore, the alternative hypothesis is that the difference is greater than d sub 0. Now, this is a one-tailed test. Now, if you notice, the direction the inequality points in the alternative hypothesis is where the rejection region is in the distribution. So this is a one-tailed upper test. So the final type is the opposite of that, where the difference between the two means is greater than or equal to d sub 0, or our hypothesized difference. And therefore the alternative is that the difference is less than d sub 0. And again, this distribution is one-tailed as well, but it's in the lower tail. So the inequality points to the left in the alternative hypothesis, therefore that is where our rejection region is. The null hypothesis and the alternative hypothesis are mutually exclusive. They have to cover all areas in the distribution, and in the one-tailed case, the inequality in the alternative hypothesis points to the rejection region in the distribution. So what about our cost center hypothesis? Now the tentative assumption, the null hypothesis, is that no difference exists between the mean call lengths at the two cost centers, so d sub 0. So in this case, d sub 0 is 0. So here is our hypothesis. So mu sub 1 minus mu sub 2 equals 0 is our null hypothesis, or our assumption. And then the alternative hypothesis is that mu sub 1 minus mu sub 2 does not equal 0. Now we'll choose the standard significance level of alpha equals 0.05. Now since sigma is known, we will use the z distribution in our test. And this is an important point when we're looking at these series of videos. Again, when we know the sigmas, either it's given to us or we know them from previous experiments or from previous data, we're comfortable with them. If we know the sigmas, we will use the z distribution and not the t distribution. We'll get to that in later videos. So what is our decision rule when we go to do our analysis and interpret the conclusion? So since alpha equals 0.05 and we're using the z distribution, our null hypothesis will be rejected if our test statistic is greater than a z of 1.96 or less than a z of negative 1.96. Now why is that? Well, it has to do with our z-table. So if we go to our z-table or do it in Excel or a TI calculator, wherever we might have, the z-distribution for a 95% confidence interval, so 2.5% in the lowest tail and 2.5% in the upper tail, that gives us a z-score on the standard normal distribution that is plus or minus 1.96. And I'm sure in your stats class you've probably seen that already. It's good to just commit that to memory. So what is our test statistic for the difference if we know our sigmas? A good way to start is to look at our test statistic for our single mean case. So we're going to tie this into what we learned in the last playlist. So our test statistic in the single mean case was z equals x bar, which is our sample mean, minus mu sub 0, which is our hypothesized mean. And that is all divided by sigma divided by the square root of n. So the population standard deviation sigma divided by the square root of the sample size. So that is how we figured out our test statistic or our z score, our z statistic in the single mean case. Now in the two sample case or the two population case, look over here on the right. Well, it looks pretty similar. So we have z equals, and then at the top there in the blue, we have the difference between two sample means. So over here on the left, it was our single sample mean. Over here on the right is the difference between our two sample means. And then from that, we subtract our hypothesized mean difference, which in this case is going to be 0. Now, in the denominator, we have our standard error again. So remember on the left, the sigma divided by the square root of n, that is our standard error. Over here on the right, the standard error for the two population case looks very similar. There's a little difference in the exponents and the radical sign and things like that, but the basic structure is the same. So over here on the left, mu sub 0 is the hypothesized population mean. So in my introduction, I mentioned where we could test whether or not the bottles of orange juice actually have 64 ounces of orange juice in them. That would be our single case. Now over here on the right, d sub 0 is the hypothesized difference between two population means. So remember in the intro, I mentioned two different factories. We could test the mean in two different factories, then we can test for the difference to see if it is 0 or not. But the basic idea for the test statistic is the same. You can see the similarities on the left to what we're doing on the right in the two sample case. Interval estimate for d bar, which d stands for difference, so the mean difference. Again, we'll tie this into what we already know about the single mean case. So remember when we're looking at the single mean, we had x bar plus or minus some margin of error, and that's going to give us our confidence interval. Now over here on the right, now we have d bar plus or minus some margin of error. And d bar, in this case, is just the mean of the differences as compared to the mean of a single sample on the left. Now the margin of error for the single mean case is z sub alpha over 2 times the standard error, which is sigma divided by square root of n. Remember, z alpha over 2 is just the confidence interval depending on what we choose for alpha. So in our case, our alpha was 0.05. So 0.05 divided by 2. We need a z-score on each end of the distribution. That is 0.025 at the bottom and 0.025 at the top, because that's 0.05 divided by 2 times the standard error there in the red. Over here on the right, the margin of error, again, it's structured the same way. Z sub alpha over 2 times the standard error of the two sample case. So same basic structure. So when we put this all together, the interval estimate becomes x bar plus or minus z sub alpha over 2 times the standard error for the single mean case. And then on the right, we have d bar plus or minus z sub alpha over 2, and then the standard error on the right. Same structure. Whether it's x bar, d bar, the z alpha over 2 is the same, and then the standard errors, they function the same, but the formulas are a bit different because we're using two samples over here on the right. But same idea. So let's go ahead and do some of this math out. So remember, we had a sample size of 30 from each call center, and then the sigma that we're given for call center 1 was 1.2, and then for call center 2, it was 1.5. So those are our two population standard deviations. Now if we go ahead and substitute those numbers in to our interval estimate formula, we can go ahead and calculate that interval estimate. So where z sub alpha over 2 is, that's going to be our plus or minus 1.96. Those are the z-scores in the z distribution for a confidence interval. It's 95%, which is the same thing as an alpha of 0.05. For the standard error calculation, we just substitute the numbers we have at the top into the formula down here towards the bottom. Now, when we go ahead and do all that math out, we have an interval estimate that is d bar plus or minus 0.6874 minutes. Because remember, our estimate here is in minutes. So here is our distribution. So we have 95% confidence interval there in the middle. That is our non-rejection region. If our test statistic falls in that region, then we would fail to reject our null hypothesis. And we expect 95% of the sample differences to be in this region. So all the D bars, we expect 95% of those differences to be in this region. Now remember, our interval is bounded by z plus or minus 1.96 because that is the boundary of the 95% confidence interval in the z distribution. Now we have our interval estimate. We calculated that down here in the lower left. So it's plus or minus 0.6874 minutes. So whatever our difference is, assuming a sample size of 30 for each call center and the same population standard deviation, which we would assume since it is the population standard deviation, the interval estimate around the difference will be plus or minus 0.6874 minutes. So the next thing to do, obviously, is to calculate our z statistic, or our test statistic. So here is our information. And again, all this is just given to us as part of the problem. We didn't actually do the sampling or anything, it's just a given. So both sample sizes were 30. The sample mean for call center 1 was 11.91 minutes. The sample mean for call center 2 was 12.02 minutes. And then the population standard deviation, or the sigma, for call center 1 is 1.2 minutes. And then for call center 2, it's 1.5 minutes. So here is the calculation or the formula for our z-score, or our z-statistic, our test statistic. So we have x bar sub 1 minus x bar sub 2 minus d sub 0 in the numerator, and then in the denominator we have our standard error. So all we have to do is substitute the numbers from the table at the top into this formula at the bottom. So x bar sub 1, that is the sample mean for call center 1, that's 11.91 minutes. X bar sub 2 is the sample mean for call center 2, that's 12.02 minutes. And then we subtract our hypothesized difference, which in this case is 0. Now in the denominator we have our standard error. And again, we substitute everything in from the chart into the formula at the bottom. So sigma squared sub 1 is 1.2 minutes. That's the sigma from call center 1. Then divide that by the sample size, which is 30. Then the sigma squared sub 2, that's the sigma for call center 2. We substitute that in as 1.5 squared divided by 30 as well. Now we go ahead and do all this calculation out and we get this. Z equals negative 0.31. Now what does that mean? Look at the numerator first. The difference between the two sample means was negative 0.11 minutes. Now what about the denominator? 0.3507 is the standard error of the distribution of differences. Now what does that mean? Well, remember, the standard error is the standard deviation of the sampling distribution. So 1 standard deviation away from 0 would be 0.3507 minutes. Now 2 deviations away would be twice that, so 0.7014 minutes. So the standard error is just a measure of a standard deviation in the sampling distribution. So when we go ahead and divide negative 0.11 minutes divided by the standard error of 0.3507, we get a z-score of negative 0.31. The negative 0.11 minutes is 0.31 z's below 0. And again, we'll see how that works in the next slide visually. But remember, we're calculating a z-score here. So this is everything we had from the previous slide. I just transferred it over so we can see sort of how everything fits together. So we have our distribution here. We have our z criticals plus or minus 1.96. That's everything we had before. Therefore, in the tails, that's our rejection region. In the middle, it's our non-rejection region. So we need to see where our test statistic falls in this sampling distribution. So the z of negative 0.31 falls about right there, where the yellow circle is. It's about a third of the distance from 0 to negative 1 in the standard deviation in the sampling distribution. Because remember, we said that the distance there is one standard error. So what do we do here? Well, the conclusion is we fail to reject our null hypothesis because this falls in the non-rejection region, in the blue region. Now there's also a bit of common sense here, and I always encourage the students I work with to use their common sense. If you notice, the cost centers have the sample mean of 11.91 minutes and 12.02 minutes. Now they also have very similar sigmas. So common sense would tell you, do you really think those two sample means are different from each other, given the random error that's in sampling? No. Your common sense would probably lead you to believe or expect to believe that this would be the outcome. Now, of course, you would always conduct the analysis to figure it out for sure, but always use your common sense when doing these type of problems. These sample means are 0.11 minutes apart. So they're like 6 seconds apart. So we would not expect these to be significantly different from each other. More specifically, we would expect these differences to not be significantly different than a difference of 0, which is what we were testing in this test. The sample results do not offer sufficient evidence to conclude the call centers differ in their mean call length. And again, we did that by finding our test statistic, our z-statistic, which is basically a measure of how many standard errors the difference is from 0, and then if it falls in this non-rejection region, we fail to reject our null and conclude the call centers don't really differ in their mean call length. Okay, so that wraps up our first video when talking about the difference between two population means. And again, remember, this was the specific case where we knew or were given both sigmas from the populations.